Okay students, today we are going to discuss about a Colpitt'S oscillator. The circuit diagram is shown here, and this is an amplifier section, and there are two sections are here. So basically Hartley and Colpitt'S oscillators are divided into two sections, amplifier section and tank circuit. Let us understand this, how this circuit will work. As we know that the Hartley and Colpitt'S oscillator consist of two sections, amplifier section and tank section. Each section is responsible for producing 180-degree phase shift of AC output voltage. So the waveform at the output of oscillator is like a standard sine wave when the time it leaves from the oscillator. When the power supply is given to the circuit, transistor will turn on by a small noise voltage as a biasing voltage. This causes the collector current to grow up, thereby capacitor C1 and C2. C1 and C2 starts charging. Once these are fully charged, they are start to discharge through an inductor by setting up a damped oscillations. So damped oscillations means vanishing slowly from maximum to minimum in the tank circuit. Therefore, AC voltage is developed across the combinations of the capacitor. These oscillations across C2 is applied to the transistor base emitter junction. These oscillations are amplified and phase shifted by the transistor amplifier. Thus, at the amplifier output, sustained undamped oscillations are produced. The frequency is calculated in Colpitt'S oscillator is as given show here. F is equal to 1 divided by 2 pi root LC, where C is equal to C1 C2 divided by C1 plus C2, because two capacitors are connected parallel. Thank you for understanding the working principle of the Colpitt'S oscillator. So as a next part of this experiment in the Colpitt'S oscillator, circuit diagram copying on schematic as a breadboard. How to copy that circuit diagram exactly on the breadboard, and how to measure the DC conditions. This is very important here. We have to maintain the DC conditions in active region. For that purpose only, you can check out in the design part, and I will explain how exactly we are going to measure and how much roughly voltages we have to get here. See, what you have to do is, in the beginning, you need not to rig up all tank circuit and all those things. You have to rig up R1, R2, RC and RE. This CE is not required while measuring the DC conditions on breadboard. So rig up as is shown in the, assume that this is a breadboard, where see that R1 and RC is connected to VCC line, and R2 and RE is connected on the ground line. Just connect as it is, and a transistor, base, collector and emitter as it is. This is optional, the variable part is optional to get the output without any distortion. So we assume that we are going to connect this directly to the RE. So we have to understand that a transistor will start to conduct when some conditions we have to maintain by designing this circuit, where this Vbe, that means the base to emitter voltage should maintain always 0.5 volts. So this is possible by designing or selecting the proper value of R1 and R2. So this we are going to see practically now. Vbe should be 0.5. Because the amplifier is designed as a collector current as 1 milliamp, that one has to be checked, and we have to say that the voltage between collector and emitter directly on the transistor collector and emitter should be half of the VCC voltage. This we have to maintain this voltage exactly half of this VCC voltage. That one also we are going to measure practically. And finally VRA. VRE is the voltage across with respect to ground. So we are going to measure different voltages And see that the next part, the schematic amplifier, here it is. So the schematic circuit diagram looks like this, and we are transferring this on a breadboard like this. As it is, just replace, mount as in the circuit diagram, R1, R1, next one R2, RC and RE. Switch on the power supply, take a multimeter, with respect to ground you have to measure the different voltages. So before starting that measurement, just I will show you what exactly you are supposed to measure. See this, the next part of this circuit. Here is a few sort of readings I took, tabulations of the DC voltages like this. So take a DC digital multimeter or analog, whatever it is available. So switch on the power supply, set the VCC to 5 volts as it is. So I measured with respect to ground. With respect to ground means this is the circuit, this is the ground part here. See that. Keep the negative terminal at the ground part and measure the other voltages in the same pattern as in this tabular column. So here VCC means the VC voltage what we are going to measure connected RC and R1 with respect to ground. So that should be 5 volt because we designed the circuit keeping the VCC at 5 volts. Next, we have designed that IC voltage, the collector current, as 1 milliamps. So I took this, I measured this reading, I got 1.05 milliamps. That is correct. See, the IC is measured between RC and a transistor emitter. Just break this connection temporarily, this part. Just break this connection temporarily, measure between collector and RC, second end of this one, you will get IC value. So this should be 1 milliamp here. Next one. So VCE. So VCE, what I got, I already explained that VCE should be maintained off of the VCC voltage. So practically, as per my design, I got 2.2 volts. Okay, that is adjustable, acceptable. It is roughly close to the half of this value. Next, you have to measure the Vb. Vb means the base voltage with respect to ground. See that DC voltmeter between base and ground. I got 1.1 voltage. That's correct. Then VBE. VBE means with respect to ground, the base voltage, DC voltmeter between transistor base and emitter is 0.5 volts should be maintained, because this will make the transistor in a conducting part. So this is very important. We have to maintain this because base to emitter will become forward bias, thereby the signal collector to emitter will start to flow. Now see the last one. Another two important parameters you have to note down. VRC. VRC is nothing but collector resistance voltage. So the DC voltmeter between ground and collector, which gives 2.75 volts here. You can also measure the VRE, that means the voltage between ground and emitter resistor. So this should be around 0.5. So totally in this amplifier section, just monitor this. So VCC is 5 volt. So we measured this RC, and we also measured between VCE, and we also measured VRE. So if you add all these three voltage, it should be roughly close to this 5 volts. That means your circuit design is correct. Now we got the readings. DC voltage is exactly the same according to this chart. So go through it and tabulate it, and let us see practically how we are going to do this one. Okay, now we are going to start rig up the circuit on the breadboard. I already explained that a very simple method of rig up the circuit on a breadboard is to just like a copy and paste. So the circuit always will remain in front of you, just you have to copy it. Now you see that I have wrote on this paper just like a breadboard. Assume that this is a breadboard here and it's a circuit. Just I am copying this as it is. You see that R1, R2 transistor as it is, there is no change at all. So if you do like this, 100% sure you will get output without any mistakes. So here there are two parts are here. One, you can see that this is an amplifier section and this is a tank section, and this is called a positive feedback circuit. So you will get the output on this case. This is how you are supposed to rig up on the breadboard. Now I will show you how exactly practically I adjusted this. This is what the amplifier section. Using this section you are going to measure the different voltages as I shown. Once again I will show that these are the different voltages you are going to measure. Okay, now I am going to show you how to measure this, and you see that this is R1 as in the circuit. There is no different at all, you see that. Only amplifier section, you see that. Now you can see that R1 and R2. See, this is R1 and this is R2. I am just replacing the same values as it is, and this is the collector resistor and emitter resistor. Now we are going to connect this to a VCC line as here, and a ground line here as here. Switch on the power supply. Then by using a DC multimeter, I will show you how to measure this. So let us understand the DC multimeter settings here. So this is a multi-purpose DC digital multimeter. Here you can see that there are common terminal here, and if you want to measure the IC, you have to connect the positive terminal to this place. With respect to this only we can measure this one. So this is a common point and you can measure with voltage. So we are going to connect these two, and I will show, and you are supposed to select this to DC voltage, and we are going to cross check practically how to check the DC condition. If these conditions are satisfied, you will get the output, that means Colpitt'S output as a sine wave here. You will get 100% perfect. So the connections I will go, just now I have shown that how this amplifier section is connected. Okay, let us see in the next part how to measure the DC voltages practically. Okay, in this part we are going to study how to rig up on the breadboard. Say I assemble the circuit as shown in this diagram. See that? It is very simple. Just copy the circuit, mount the component as in the circuit. I am 100% sure that you will get output. Do not connect here and there and make a jungle like that. Okay, make a simple and easiest method. So this is one of the easiest method I used to practice. So I never failed the outputs because I made a simple techniques. So the transistor here it is shown. Now I am going to show you the practically how I assembled here. You can see that. So in this case, so as in the circuit diagram, R1, R2 and RC and RE. I just no capacitors are connected because we have to measure the DC conditions. Now you see that I connect with respect to ground. This is ground connection. I switch on the power supply and set the VCC because my design is 5 volts. I measure DC as a 5 volts here. Okay, so VCC is 5 volts here. Now you can check it in this chart, tabulation of the DC voltages. VCC is 5 volt. Okay, so I will measure the IC next step. Okay, what I have to do, because in this circuit diagram, it is directly connected to the collector. So the current passing through this collector circuit, I have to break this resistor temporarily. In between I have to connect a milliammeter and it will show the DC current. That means, okay, let us check this. Okay, now you see that I just break this collector circuit here. I just removed and kept some apart from this. I can zoom and show you here. Okay, so here I removed this collector circuit here, little bit away, and in between I collect the collector current meter here, and you can observe this also. See that for the current meter I have to make a small changes here. So the common terminal will be here. Earlier I while measuring the DC voltage it was here. Now I shifted this to current mode, and we have to change this rotary switch to the milliamps range. Now it is measuring the current which is flowing through the collector. So as per my design, I already told you that my design is 1 milliamps. You can check the design part from the link, and it is 1 milliamps. So practically I got 1.06. So theoretical design is 1 milliamps, and practically also I got 1 milliamps. Now let us measure the remaining part of the voltages of this circuit. Okay, next part. Now I change again DC milliamps to DC voltage. Now I change this rotary switch to milliamps to DC voltage. Now we are going to measure the other remaining voltage. See, in the third part, in this chart, I am going to measure now VCE. That means the voltage that the DC voltmeter should be connected between collector and emitter, and this voltage should be off of this VCC voltage. Then only our design is correct. Okay, now you see that the voltage between the emitter and collector is, I already explained you that we have to maintain this voltage should be off of the VCC voltage. VCC voltage is 5, and now you see I connected across collector and emitter, and it is what I getting practically is 2.2 volts. So it should be roughly off of the VCC voltage. Okay, let us go for the next part. Okay, so the next parameter we are going to measure Vb. So Vb is measured between, the voltmeter should be between base and ground. Now you see that the ground connection is here, and the voltmeter is connected to base. So according to my design, I have to get 1 point something. So I got 1.1 volt here. Okay. So let us go for the VBE. That means VBE voltage should be always maintained 0.5 volts. This is very, very important for any amplifier design. So the voltmeter should be connected between base and emitter. Let us see how much we will get practically. Okay, let us see now. This VBE should be 0.5 something. Now I connected the circuit between the voltmeter between base and emitter. They should be maintained 0.5. See, practically I got 0.586 something. So that is perfect. So our design is 100% perfect. And the last one we are going to measure VRC and VRE. VRC means here with respect to ground, the collector voltage and emitter voltage. So I am going to connect this now, and let us see. So VC voltage I got 2.2 volts. So it is nothing but I got earlier that is 2.75. Okay, this will do properly. And one more thing we can measure, the last parameter is emitter voltage. So emitter voltage can be, it should be some 0.5 something you are getting. It is too less voltage. This is what I am getting here. Okay, now you see that VRE, so the voltage between emitter resistor with respect to ground. So we have to get 0.5 something, and see exactly I got 0.518 something. So this shows that our amplifier circuit is working and designed properly. Now we have to recap the tank circuit, and you can see I already explained how this oscillator circuit, Colpitt'S oscillator, is generating a sine wave. And we are going to recap the circuit as shown in the circuit diagram. So you can go through it, you can take a one snapshot if you require, and recap as it is, and you can see the output. Let us see the next part, how to recap this and finally get the output. From there, how to measure the frequency. Okay, so today we are going to complete this experiment. I already show how that the components are to be assembled and the DC conditions are to be step by step in a detailed manner. And this method is also common, particularly this amplifier section for crystal oscillator also. And addition to that, common emitter amplifier with and without feedback. This part is common. you can measure the DC conditions, everything is same as it is. Only the difference in this oscillator here is a tank circuit. So in the tank circuit, I already explained how this it works and how that 360 degree phase shift, that means 180 360 degree of that transistor will do one part and the another part will be by the tank circuit, and finally you will get 360 degree output as a sine wave, and the frequency is calculated by using this formula 1 divided by 2 pi root LC, where C is equal C1 C2 divided by C1 plus C2. Now after connecting the tank circuit, we are supposed to connect this part, because we made this into two parts, amplifier and tank circuit. So this connection is very important. Addition to that, we have to complete this loop, this part, and connect the CRO to the collector part, and you can see the output and undamped oscillations and calculate the frequency and amplitude. Now you see that the components, before connecting the components on the breadboard, I have made a diagram here, assuming that this is a complete breadboard like this. This is a IC slot where I made a shade here, and assemble the component as in the circuit diagrams. Do not change anything, the positions of the components also. You can see that 38, it is 30. Next to that 13K, it is 13K. I think you understand this. Just copy and complete the tank circuit. So I made this like in this way. For your more clarity, I will expand this, zoom this, and just I think it is enough. Now you can see that this is R1 and these two are the coupling capacitor, collector resistor, and emitter component here, the emitter capacitor, and this portion is nothing but a tank circuit. So 330 and 220 picofarads and one inductor of 220 microhenries, and it is connected. You see that this wire actually connects the amplifier to the tank circuit, and a loop circuit is connected, output of this to the base of the amplifier. Now let us see how exactly the output will connect, and roughly around 1000 kilohertz will generate for this tank circuit value. Let us see the demonstration and the output on the CRO. I am assure you that you will get output at one shot if you follow this method. I cannot explain the amplifier design and this detailedly because this video is little bit longer. Please go through patiently, because it will help you for CE amplifier and crystal oscillator and all these things. So otherwise the video will be short. Okay, so for the next part we will see that a video on displaying the output on the CRO. Thank you. So I assembled this circuit as per our diagram, and this is this part is an amplifier section, left part. This is an amplifier section, and this is tank circuit, and the connection between that amplifier and tank circuit is this one, and one positive feedback wire is connected to this, and the output is connected to the collector of this. As soon as I switch on this, I already explained how exactly it generates sine wave, 360 degree, 180 degree phase shift by tank circuit, and another 180 degree by the transistor. As soon as I switch on this, see the output on the CRO like this. Okay, so we can adjust the distortion by using that potentiometer I connected. See that as I am increasing this, adjusting the part, I got some kind of distortion here, some kind of distortion that can be avoided by adjusting the 1K part slightly. Okay, you can fix this. Now you can measure the amplitude between two peaks and the clock between one complete cycle, and can be concluded. So the frequency can be calculated. F is equal 1 divided by root LC, where C is equal to C1 C2 divided by C1 C2. You can calculate the frequency by varying the inductance value here. The inductance value, you can generate different types of frequencies, and I think you will understand this experiment and the theory behind that oscillators. And the amplifier design is common for Hartley, Colpitt'S, RC coupled amplifier without feedback. Thank you very much. I hope this will help to get the output in the laboratories. Thank you very much. Thanks for watching the video. Share with your friends and comments. Thank you very much.